now to introduce you to some of the major rock types. That's going to be a key thing that we'll discuss into next class period. And so we're going to start with a few types of formations that they're not a specific kind of rock necessarily. They're not like limestone or sandstone, but these are just kinds of deposits that are not really consolidated into a pure mass. And so we call these unconsolidated formations. So here's a few of them that I want you to kind of be considerate of. Number one, you could have what's called loess, and that's a complicated looking word there, Loess. And loess is basically just a very fine wind-blown sediment. We're going to come back and talk about it a lot. So you don't have to memorize it now. Just know that I want to expose you to it, and we'll come back and touch on it. But it is so fine and wind-blown, it's like flour. It just kind of blows in the wind. And that actually is the key to where you find loess deposits. They are formed because they've been blown into piles of sediment by winds at some point in time. Gravel deposits. We've all seen, gravel deposits, of course, on gravel bars of streams, but oftentimes, particularly in places nearby here, like Land Between the Lakes, National Recreation Area, or if you live in some of the counties southwest of Clarksville, like I live in Dixon County or Humphreys County, those counties, a lot of the hilltops are capped in these layers of gravel, which used to be the ancient coastline of America about 90 million years ago. Down along river floodplains, you can have alluvial deposits where these are very recent sediments that have been laid down by the floods of rivers over time. So these are mostly silts and sands that have formed these alluvial floodplains. In a lot of West Tennessee, you have very deep deposits of sand formations that have built up over time. And then finally, on some of the mountain slopes, particularly where you have very steep mountainous lands, you can have extensive deposits of what are called colluvium. Colluvium is where you have these sort of jumbled masses of cobblestones and boulders that are largely breaking off of the rock faces or the mountaintop and just sort of tumbling down and they sort of form a blanket over the mountainside. And so these rocks really originate upslope. And they're very different from the rocks sometimes that are immediately actually part of the bedrock underground. But these are loose rocks that have sort of just made their way by gravitational pull down the slope as they've just sort of been tumbling down over time. So this is called colluvium, and it's a term we're going to need to think about. Just a few images of these. So here's some close-ups of gravel beds. Again, this is not consolidated rock, right? You could easily take a shovel or a pickaxe and just kind of dig into this. So it's not like you're trying to bust up into a solid bedrock layer. These are obviously beds of unconsolidated materials. Now, the bulk of what we're going to talk about next, and I think what I'll do is just sort of introduce this for a bit, and then I'm going to stop and see if there's any questions. Where we're going to pick up next time is we're going to introduce the actual specific kinds of rocks. So we'll start with sedimentary rocks. Then we'll probably get into the metamorphic rocks, and then we'll conclude with igneous rocks. And this will take us through pretty much all the lecture next Tuesday will be devoted to the second part of our geology introduction. And then once we're done with geology, then we can move on to other topics, and we will have at least introduced it as a foundation. Now, as part of us meeting in class, I also have a lot of these rocks, which I'm going to put out, and you'll be able to touch them and feel them and kind of, at least the basic important types that you ought to know. So when we begin next Tuesday, we'll start with sedimentary, and a lot of these are really common rock types around here that I will introduce to you. And I will definitely expect you guys to sort of be familiar with the basic types. As I said, you can get real complicated with geology. It gets real complicated real fast. I just want to give you a good working knowledge so that you have enough to be dangerous and to work with, and to where you can understand the world around you. let me stop there. Let me ask everybody if you don't have to, but those of you who want to turn your camera back on, if you want, let's just have a quick couple minutes to debrief and discuss. And I would like to know if, how you guys are doing and if the pace of the class so far is okay. And if there's anything that you'd like to tell me or anything, go ahead. How you guys doing out there? Is it making sense?
Yeah.
Awesome. Cool. Good deal.
Yeah, it's cool.
Pace going okay?
Definitely making sense. I think it'll be a whole lot easier once we're actually, lecturing in person.
Yeah. Absolutely. And in person, it's more fun. We're all kind of carrying on and discussing, and I can see you all. It's a lot better that way. Okay. All right. Any questions about any of the content we've covered, or anything else about the class as I've sort of laid it out to you? Awesome.
I didn't.
I do have a.
Go ahead.
Or, you can go ahead.
I wasn't prepared and didn't take notes about the periods that you were and the certain ones that we needed to know.
Uh-huh.
Is that in a syllabus or in a assignment somewhere? Review?
It's in all the materials I get. So one is it's in that geology chapter that I wrote. It's
Right.
in your text, it's in the book, right? And then of course it's in the PowerPoint, and I'm going to give you a recording in the PowerPoint. So that's, I feel like between all that stuff, it will take, and that's a good question. I think in that case, it's going to require just a little bit of focused memorization on your part. But then I'm going to touch on that stuff so much this semester that, you're not going to have any choice but to get it. But what I would rather you do is make sure you go ahead and spend some time forcing it into your brain so that when I say it, and when I say the time periods, you are already kind of thinking about, it's about 90 million years ago, right? The quicker you can get that, the quicker it's going to make sense to you.
Okay, great. The arrows and the periods and the years.
And the epochs of the
Epics,
Cenozoic era. Yeah.
epics, periods, years. Thank you.
You got it. Any other questions?
I did have one.
Yes.
When you're talking about the depositional environments, that was a little unclear for me.
Yeah. Again, all we're really thinking about is where do sediments collect naturally on the landscape from erosion, like versus where are they being washed away from, right? So that's where they're eroding from. We want to know where are they going to, because where they're going to, those are the depositional environments, like ponds, bogs, coastlines, alluvial plains. And then if you know what the depositional environment is, then you should be able to predict what type of rock would form there eventually under the right circumstances, right?
How do we link the geology back to what most of us in this class are interested in? The species, the ecosystems, the ecology. Well, I hope it's going to be evident by the time we get through this that you really can't understand all that stuff as well as you need to without a firm foundational understanding of how geology structures everything. If Brandon is, we need to know our rocks. It's surprising how many people don't know the basics about the rocks of the world that they live in, and that really drives everything. Okay, so let's start there. All right. So first of all, we're going to talk about three major groupings of rocks. Let's say them with me: sedimentary, metamorphic, igneous. All right, is that pretty much, have y'all had that at some point? Probably all the way back to elementary school in some form or fashion, right? Good deal. Okay. And then the rock cycle connects all those together, right? Remember how we said you can take a sedimentary rock, heat it up, boom, it becomes a metamorphic rock, or it becomes an igneous rock. You can take an igneous rock, you can melt it up and heat it or erode it away rather, and it can become a sedimentary rock. They are all connected through the rock cycle. What I want to first talk about and focus on are the rocks called sedimentary rocks. And these are the rocks that are the only rocks that we have here in central Tennessee. We do not have any metamorphic rocks. We do not have any igneous rocks. In fact, these are the predominant rocks across the vast majority of eastern United States, except for the mountainous regions of the Appalachians, a little bit of the Ozarks over in Missouri. And then as you get up into what we call the Canadian Shield, which is around the Great Lakes and upper Minnesota, then you get into some other non-sedimentary rocks. So what are the primary sedimentary types here? They include limestone. That's a very common rock type around here. Dolomite is similar to limestone, looks very much like it. In fact, can look identical to it. They only really differ chemically, and we'll talk about that. Chert is also a very common rock type, easily confused with limestone. Is this too much light or is this okay? Good. All right. Sandstone. It's common in some areas of the state, but not common here. In fact, it's generally absent from most of Middle Tennessee. Shale is a fairly common rock type. And then siltstone is one that's not that common. You got to really know where to go to look at it around here. If you're in parts of the Appalachians, siltstone is very common. And there are others. These are just some of the key ones that are sort of the most common. Now, some of the other ones that we'll become familiar with here are shown on this table. And this is sort of a general way that we can sort of group sedimentary rocks. And we call them sedimentary rocks because they're formed, right? They form by this sort of concretion process where they become hardened or lithified as a result of small particles of sediments becoming united together into a rock. Okay, now that may not be the best geologic explanation of rock formation that I'm sure Ken probably would get from a good class in geosciences. But again, hey, remember, say it with me. I only play a geologist in the movies, right? Okay, cut me some slack, right, Ken? All right, so, but generally sedimentary rocks are forming because of the accumulation of sediments. So what do we mean by sediments? We're talking about pieces of clay, pieces of sand, pieces of silt, right? These little fragments of materials, all right? Sometimes gravel, all right? It can be on the larger end of this. So we have these rocks that are formed by the accumulations of sediments. We can divide those into a group called clastic rocks. Okay, that's a good term that will help connect you to the geosciences world. Clastic. Among that group, you'll see then they are formed, different rock sizes are formed of different particle sizes. So those that are less than 1/256th of a millimeter, that's the smallest particles, right? Those are the ones we would say are your clay minerals. These are ones that can hang suspended in water. They don't really filter out very well. Like think about even a sand grain has enough weight that it will sink to the bottom of a body of water and settle on the bottom. But these clay particles just kind of float around, you know, and they eventually settle. So they're very lightweight. And when these solidify, they form a type of rock, which is not too common, called claystone. Right. Slightly bigger than that, we have things like, you know, grains of quartz sort of mixed with clay minerals that are a little bit sandy in texture. These solidify to form a rock called siltstone. In fact, you can tell these two apart by scraping it on your tooth, for example. I'll tell you more about that in a bit. If we step up the particle size a little bit more, you've got a couple other types. The one that I'll point out there, if your grain is between 1/16 and 2 millimeters, you've got basically a sand grain, and that sand is formed of quartz, maybe another type of mineral called feldspar. We do not need to get too deep in the minerals in this class. That's a little bit deeper than where we need to go. But basically, if you can recognize what you think of as a grain of sand, put all that together into a rock, a lithified structure, we have sandstone, okay? And then these last two types, I'm just going to point out the bigger one there, is when you have sort of formations of larger particle sizes. Usually, like think about pea gravel, you know, maybe a little chunk of a cobblestone, bunch of sand. So it's a lot of fragments of different sizes. Some of them are quite large. They form into a rock type called conglomerate. We're going to go over these multiple times, so I just want to kind of introduce you here. Then we have a whole section of rock types that are both chemical, that's one group that's separate from clastic. And these are rocks that form through chemical processes, right? So some good examples here include chert, dolomite, and limestone. You'll see me often refer to dolomite and dolostone sort of interchangeably. It's probably technically correct to call that dolostone. Dolomite is usually the mineral that makes up dolostone. But sometimes it's very common to use those sort of interchangeably. But basically, these three rock types form where certain conditions, let's say in the ocean, you have certain types of chemicals that in solution that precipitate out and accumulate and form that precipitate eventually hardens into rock. That can become chert, it can become dolostone, or it can become limestone. But it's a chemical process that's driving that through precipitation of these certain types of solutes rather than the accumulation of particles, okay? And then the final type is when you have biological material. So let's say, for example, if you've got oyster shells that pile up onto each other, right? They get eventually compressed into a type of limestone that's all fossils. Or you may have, in the case of coal, you may have a bunch of peat moss and parts of trunks of trees and leaves, and all that living material gets squashed and sandwiched and eventually forms into coal, which is developed from living material. So these are biological sources of types of rocks here. These are chemical, and those are clastic. The ones that are outlined in red are by far the most common types of sedimentary rocks for the Mid-South region, which is kind of where we're focused. So let's just look at some of these and talk about some of their characteristics. And then when we have our first break coming up in a little while, I'll have some of these rocks back on the back of the room, and then you can go around and feel them and touch them and all that kind of stuff. So the first type here, which is a clastic type, again, it's formed of particles that accumulate together. It's called shale. And for us in this region, shale is not super common. It usually forms a layer that's sandwiched between other rock types. Good place to see shale, for example, if you're driving to Nashville, right? Everybody knows where that is. You go to Nashville, you sort of drop off the hill that we're on here. Clarksville's up on this big elevated sort of plateau. And as you get to Nashville, before you get to Old Hickory Boulevard, you drop down about 200 or 300 feet into a valley. As soon as you get to the bottom of that valley, as you're driving down the valley, what you'll notice is there are layers. I'll just sort of draw you a little three-dimensional model of what I'm seeing, what I'm showing you here. From this plateau surface, if you were to look in the rock layers of the road cut that's been made along the highway, what you would find is that all this rock up here is of one type, and that type happens to be chert. And then down through here, there's another rock, which is limestone, all the way probably down to here. I'll just sort of draw the limestone. It's having those diagonal lines in it. And then down here is limestone in the very bottom. So all this is also a limestone layer. Okay, but this little band right here is a chert layer, and it's only about 10 feet thick. And that, I'm not chert, I meant shale. It's about a 10-foot thick band of shale, and it's largely hidden from sight because it's obscured by having all these other layers on top of it, right? It's sandwiched and buried down there. But that layer is really important. And it's very thin, and so shale, as you can see here, is easy to break apart. If you were to smack it with a hammer, or if you break it with your hand, it just cracks and falls apart. And there's a term that we also use called fissile, which means, and that's spelled Fissile, and it's basically means it can be cleaved such that you could just kind of open it up into very thin sheets, right? It's a fissile material. And you can kind of see that by how it breaks apart into those flattened sheets. How many of you who, maybe you're knowledgeable of this, maybe not, how many of you have ever said, maybe you've had a home inspection and someone says, y'all really need to get a radon test because radon is like the second leading cause of lung cancer in the United States. Anybody ever told you need a radon test in your house? Yes? Okay. Particularly in your basement area. And the reason is that this layer of rock, and you can see it has almost like this blackish sort of appearance to it. This layer was formed when this area was in a slightly deep sea called the Chattanooga Sea. That was the name of it. And this was like, you know, close to 460 million years ago. And that sea was very, it was quite deep for this region, and there was very little oxygen, but there was a couple things that were really abundant. A lot of uranium, which is a fairly rare element, right? And a lot of radon. And so that radon that is being emitted into your basement spaces or your crawl spaces of your house is largely coming from this rock layer. Now, if you're at Nashville, you're kind of lucky because you don't actually have that layer below the city of Nashville. So you probably don't have anything to worry about. But if you live in Dixon or parts of Clarksville, that layer is underneath you, right? Because if you're in Nashville, you're down here. But if you're up here at, you know, Springfield or Ashland City or some of those things, that layer is near you, and it is emitting those harmful substances. And so that's one of the things we have to sort of mitigate for. And so shale is an important rock, but it's not super visible in many places unless you know what to look for. All right, here's another rock. This is claystone. If you look at this, you can almost see it. It looks like just piles of clay that have sort of solidified, right? And these are often very soft rocks, very easy to break. You know, you can see a lot of it's crumbling there on the face of that exposure right there. How many of you have ever dug in your backyard and you can be like, maybe you're planting a tree or burying your dog or something, right? And you're like, oh man, this is hard digging. There's a lot of clay down there, right? Well, you know, you're obviously digging through the subsoil, in some cases the topsoil, and it's not like you're trying to go through bedrock. But just imagine if that clay layer, which is actually soil, right? It's already hard enough to dig in. Imagine that clay layer solidified, right? Then you would have something akin to claystone. Now, to be able to differentiate this from the next type of rock, which I'm going to show you first, and I'm going to talk about the differences. The next type is derived not so much from clay particles, which, remember, clay on that table of particle size is the very smallest, right? But the next size up are grains of silt mixed with a little clay. And those are slightly bigger, and they give that rock different properties. They sort of feel the same texturally. They're both easy to break. You pop them with a rock hammer, they just fall apart. But they are very easy to differentiate siltstone from claystone by what's called the tooth test. So if you got a piece of this rock, you can actually rub siltstone against your front tooth and it feels gritty. You can definitely feel it. That's kind of wild. My wife's like, you sure you want to do that? I was like, I don't mind. But with claystone, it's very smooth to the touch, real smooth. You're like, wow, that's like satin. And you put the siltstone up here like, oh, okay, yeah, that's going to rub some enamel off and do some damage. Let's don't do that again. Okay, another very important rock. So I would say this, that siltstone and claystone are minor rock types that you're just not going to see a lot of. And here's why. Because they erode so easily in the span of time that they erode away. They're carried away into streams and out to the ocean, okay? Where you will see them is that if you have a mountain that's been turned up on its side and you look in the edge of that mountain, right, on like a cliff line, you'll see it as a seam in the rock layer. But one of the real reasons why it's important to know about claystone and siltstone is because of how easily erodible they are. They often are where valleys are today. Remember we talked about that concept in class last time? That if you've got a super easy to erode rock, you can expect that valleys will form in that rock type. So a lot of times by looking at where valleys are, you can sort of project back and say, oh yeah, there were soft rocks here before this valley formed. And maybe those rocks were in things like shale, siltstone, claystone, or even limestone, all of which are relatively easy to erode. Okay, this next rock type is also a clastic type, again, formed of particles. You can see all those particles very easily. And these are sand grains made of quartz. That's the mineral. And they are cemented together with another mineral called calcite. Again, you do not need to know the mineral names. We're not going to get that deep. I'll just throw them out there for your knowledge. Now, the book that you have, which I very much want to make sure that you are reading it, right? You've got quite a bit of material you need to get through by Thursday. That book is exceptional at explaining all this stuff, richly illustrated. So be sure that you're staying up with the reading. Sandstone is a very erosion resistant rock, relatively speaking. It's hard. Yes, there are types of sandstones where you could take a screwdriver or a pocket knife, and you've probably seen this. If you go to some type of sandstone overlooks, for example, a lot of people will vandalize those, not only by spray painting them, but by taking another rock or something, and they'll carve their initials in it, right? And you can easily, you know, carve your initials in it. LDE loves so-and-so right there in the rock. And while it is easy to carve into, relatively speaking, it still is a really erosion resistant rock compared to these other ones that we've been mentioning. So at the end of the day, why does that matter? Well, a ridge formed of sandstone will become a ridge or a mountain. It will stay that longer compared to a valley adjacent to it with a softer rock type, right? That's going to determine what remains an elevated topographic surface like a mountain or a ridge versus what becomes a valley. Okay. So what happens when you erode sandstone? Well, it erodes back into these quartz grains, right? Back into sand. And so if you've ever been to, let's say, parts of East Tennessee that are underlain by sandstone, the soils are very, very sandy. It's almost like sort of walking on the beach in places. Okay. This next rock type is one I mentioned to you that is composed of rocks and particles of different sizes. This is conglomerate. And again, it is a type of clastic rock. Notice on the scene on the left, you've got all kinds of mixtures of sizes of different sediment particles in there. Now, in this case, note that those particles are relatively smooth, right? What does that indicate? Yeah, they're water worn, right? They've been tumbling through streams somewhere back in time. Now, I went back and watched the video from last class just to make sure I, was, intelligible in when I was trying to relate to you guys and all that stuff. And I remember going back to a part where I said something, and I wondered to myself what you guys thought of it. And I said something about these particular grains of rock that had been sort of reincarnated, or it's not the right word, but sort of reincorporated into a new rock, that they ultimately had a life before that. And I said, maybe once upon a time, they were part of a mountain system in South America. And then they eroded off that mountain. It was carried by a river that's no longer there, right? An ancient precursor to some river that doesn't exist anymore. And instead of being carried out via the Amazon to the Atlantic Ocean, they were carried instead to the land that is now Alabama and Tennessee. Think about that. Does that even make sense? I don't know, Dr. Estes. I think you're making some stuff up, brother. So you're telling me that there's this river that used to run off of some mountains in South America, which is now like way in the Southern Hemisphere, right? Not even connected barely except for, the Isthmus of Panama. And you're telling me that those rocks washed off of some mountain range and are now embedded in the landscape of Alabama? I don't know. Like I said, I'm not a geologist. I just play one of the movies. You decide. Yeah, for sure. If you look at the coastlines, right, they look like they just fit together, right? All right, so you think it's possible. What do you guys think? Am I making this up? Am I just definitely making it up? Yeah. All right. Well, we'll get there. We're going to get there. And your book has all the extra details you want about that topic. Okay. All right. Anybody online have any questions so far with what we talked about? Everybody good?
I do.
All right, Laura, what do you got? Speak loud.
Yeah,
for me.
I'm looking at that conglomerate rock, and would you call I see the rock separated. I can visualize that and hold it in my hand as a conglomerate, right? But the bed that it came out of, what do you call? Is that whole layer called a conglomerate bed, or is it just?
Yeah, it's bedrock. It's just like taking a section out of, this section was probably just broken off by somebody's rock hammer. That whole bed right there is all conglomeratic bedrock. And
Gotcha,
usually use
conglomerate.
that as a sort of a way to qualify. Like you can have conglomeratic sandstone, for example, right? Where you
Gotcha.
can have bits and pieces of other larger non-sandstone type rocks embedded within a general sandstone matrix. But yes,
Perfect.
that's all conglomerate. Yeah.
Thank you.
All right, now let's go to a similar but different type of rock that is also made up of various fragments. There is one place, actually there are three places in all of Tennessee where you could experience this rock type and study it for a little bit. How does it differ? Well, one, what's the similarity with conglomerate? You still got chunks of big rocks of various sizes all glued together, right? Boom, that's the similarity to conglomerate. Now, what are the key differences between breccia and conglomerate? Say again? You got sharp edges versus round edges. Okay, Kian, was that, you're gonna go there? Okay. So, why would you expect that? Kian? Less travel in water for breccia, right? And give us some instances where you would expect less travel. How might you find that in nature? Okay, anybody else? Landslides, great example. Yep. Avalanches, landslides, debris slides, those kind of things can result in accumulations of rocks of various fragments that eventually those layers could become solidified or lithified and form into a rock type called breccia. Now, usually we think about breccia happening in a couple of kinds of places. Mountainous landscapes where you have very steep sided mountains, right? That experience these landslides. We don't really have those kinds of mountains here in Tennessee, do we? I mean, we have low sort of rounded mountains like the Smokies, right? You don't really have a lot of landslides. You have some, but not really that prominent. If you've been to Colorado or you've been to the Sierra Nevadas, those are steep, those are rocky, those are cliffy, and they have lots of just frequent avalanches and landslides. That's where you typically expect to find breccia. So if we don't have that in Tennessee, where do we find breccia at three places? Three very specific places. Anybody? That was more Kentucky, right? So there's a lot of faulting up there, right? Okay. What would cause jumbles of rock to occur in three specific places, all far removed from one another? In fact, all three are in Middle Tennessee. One's in Montgomery County-ish. Yeah. Anybody? Inside of cave systems? You know, that's not a bad idea. If you had a cave roof collapse, maybe. It's possible. The only thing about that is some of those rocks, yeah, maybe. That's a maybe. Let me give that, again, I only played a geologist in a movie, so I can't give you a concrete answer. Yeah, these are definitely sites where they are not associated with rocks, with streams or rivers, these particular formations. What could cause piles of rock or jumbles of rock to be in very confined spaces? Anybody? Say again? Sinkhole? Again, yeah, you could. That almost is like those avalanche type scenarios. Again, I think you're on the right track, and I'll concede that makes sense. I'm going to go ahead and tell you. Meteor impacts, right? So again, we have three meteor impact sites. One's 15 miles southwest of us. It's right on the Stewart, it's maybe in Stewart County.
The majority of it's in Stewart, but I think the edges of it might.
Edges, yeah. If you've ever been in the little town of Erin, which is in Houston County, there's a little town called Cumberland City, right on the Cumberland River. There's a big TVA power plant there. That is in the meteor impact area. Now, you cannot see the breccia at the surface, but if you were to dig down underneath the ground, and various exploratory geological expeditions have uncovered this, then you do have breccia below the surface. And that's because of a meteor impact, and it just jumbled everything, right? And so the other two are, one is in Jackson County, Tennessee, called the Flynn Creek Meteor Impact Structure. This one down here is called the Wells Creek Meteor Impact Structure. And then there's one in Lincoln County, Tennessee, called the Howell impact structure. All in Stewart County. Good to know. Okay. All right, next up, let's get out of those. So all those that we just talked about are formed of particles, right? They're clastic rocks. Say with me, clastic rocks. You got it. That almost sounds like classic rock. You know? All right, now let's talk about some of the types that are biologic rocks. So these are formed of accumulations of formerly living plants or animal material. So first example that we're going to talk about is limestone, one of the most ubiquitous rock types in all of Eastern North America. And specifically, when you look at a lot of the limestone, you can see that they have a rich assortment of fossils in them. And as we said, limestone forms in shallow seas, therefore you should expect that it has a rich assortment of marine organisms, right? Things like bivalves and brachiopods and oyster shells and, you know, all kinds of invertebrate things that have, you know, calcified shells. And those calcified shells are rich in calcium, are what contributes to the properties of limestone. Here's another scene. This, again, is out of your book. This shows a specimen of coral, like from a coral reef, that is in this limestone bed, and this is on a cliff above the Elk River in northern Alabama, just south of the Tennessee line. You can see that there. And then here's another very rich specimen of what's called fossiliferous, means very fossil-rich limestone. And you can see all kinds of different bryozoans, which are types of invertebrate animals. There's Archimedes is a really common type, has a sort of a spiral structure. One of the other things I love about your book is that it has sections in there that if you are interested in fossils, there's lots of great sort of illustrations of the most common fossils for this region. So if you want to, you know, it's really a fantastic book, especially if you're going to go on and I would keep it as a reference if you're going to teach or if you have children or anything like that. It's a great book. Okay, and then here's another kind of limestone. You do not need to know it. Okay, I'm not going to test you over it, but I want to just illustrate what makes it special. Okay, in this case, this is not a fossiliferous limestone, but rather it's formed by particles called oolites. Okay, and these look like little eggs essentially. And the layman's version of this is basically you have sort of a grain of a material, a sediment grain that becomes encapsulated in sort of calcium, and that rolls back and forth. You ever walk along the beach, like in Florida somewhere, and just watch the waves roll in? All that wave action, right? What's it doing? It's pounding the sand. It's bringing some sand out. You ever just stand in the ocean and let it kind of wrap around your feet, and it takes that sand right out from under your feet and pulls it back, right? Well, those grains of sand are just rolling and washing with that wave action. And that's kind of what's happening right here. Those sediment particles are being rolled around, almost like rolling a piece of dough, right? And those form materials called oolites. And so when those solidify, and it tells you exactly the depositional environment, right? When you see oolitic limestone, it means that that rock is forming at the contact zone of a shallow ocean where there was wave action that was forming these particles. So that's why I mean to say that these rocks can really tell a fantastic story of the history of a given site. And there's some of these oolitic limestone particles here. All right, anybody here from Mississippi? No Mississippians. Okay. All right. How about Alabama? Anybody here from Alabama? No? Texas? Louisiana? Texas. Well, Ken, I didn't know you were from Texas. All right. All right. So if you're from parts of East Texas, extreme Southeast Oklahoma, a little bit of Arkansas, Louisiana, or those other states I mentioned like Mississippi and Alabama, there's a region there that there are regions in those states that have a very specific kind of sedimentary rock called chalk. And if you happen to be from England, which I don't think anyone is here, the cliffs of Dover, which are on the English Channel facing the coast of France, are formed of very and beautiful chalk formations. Okay. So these chalk deposits are, in many cases, almost pure white. And, you know, if anybody's ever written on a chalkboard, you know what I'm talking about, right? You can feel that chalk. Well, these are biologic materials because chalk is made up of microscopic organisms of various types. But one of the main types that it's made up of are what are called coccoliths. And these are probably classified as, you know, various types of protists or other types of tiny microscopic, you know, single cellular organisms. Some of these also group into what we call foraminifera, rhabdoliths. It's a variety of groups, and in any way, they all have these calcified outer shells. If you look at them under a scanning electron microscope, you can see like the coccoliths have these very, it's almost like a sphere covered in protective shields, right? And when those die and they become incorporated into the seafloor, then they form into these immense beds of chalk in select places like Alabama, Texas, or in England. And so these particular types of minerals, these particular types of rock are chalk, and they're again very erosion prone types of rock. They're extremely calcareous, which means they have a lot of calcium. So one of the things that's going to be important to relate to Thursday's discussion is, where do we get soil, right? Soil, the type of soil that forms and the minerals that are in it and the elements depends on the geology of what types of rocks are underneath it. So as you start thinking about these rock types, think about what kind of soil does sandstone erode into? What kind of soil does limestone erode into? Okay, much in the same way as I want you to think about what is the depositional environment that you need to form sandstone or to form limestone. So start making these connections as we go. Okay, another type of biologic rock is called coal, right? We obviously know that coal is extremely important for the fossil fuel industry. I think most of us are probably a little glad that we burn a lot of coal over the past week, so that we actually had some heat in our houses through various the coal powered power plants. But at the same time, obviously, that burning too much coal is what is directly feeding to climate change right now, with the abundance of the atmosphere's concentrations building up in various fossil fuels. So what we have here is before these biological materials, which basically, if you look in the upper right, are like parts of poorly decayed plant matter, right? These are parts of like sphagnum moss or tree trunks or leaves. And these are where you have plants that are growing in a swamp or in a marsh, usually in a fairly warmed tropical environment. And as those plants are falling down on each other and accumulating in the bed of that swamp, there's so little oxygen down there that there's very low rates of decomposition. And so these things just build up and build up. And when there's almost no decomposition, then that means that those fibers of those plants and tree trunks and those kind of things, they kind of stay intact, right? Now, this is before they get compressed into this rock I'm going to tell you about in a minute called coal. But when they just sort of get compressed, you can still actually reach your hand down in that bog and pull it out, and you'll see it's this dark brown, and it's fibrous, and you can still pull apart parts of stems and leaves and moss. You can actually often still identify what it was. Even in some cases, 12,000 years later, you can still pull out pine cones from the Ice Age, 1 meter below the surface from 18,000 years ago. They're still intact because of the lack of decomposition, okay? So all that fibric material is a material we call peat. So if you go to Lowe's or Home Depot and you want to buy, if you're into gardening, you want to buy some peat moss to put in your garden, you might do that because it holds more water. If your soil is too sandy, you can add peat to it to help hold more water on that site. If you need to grow blueberries, you may want to make your soils more acidic. Sometimes you amend the soil by adding peat formations, which helps to acidify the soil. So there's lots of practical uses for that, for peat. But now what happens if you have a swamp, right? Let's imagine that, I'll draw this on the board. Let's imagine that you have a swamp here. And in that low depression where there's some water and it's mucky, in the bottom of that, imagine you're just kind of walking in, right? It's sucking at your feet. All that stuff's accumulating there. And over the hundreds of years or thousands of years, those deposits just sort of build up there, down to a depth of like a foot. Okay, well, now imagine that we go fast forward in time to like 1 million years. Okay, maybe it's no longer a swamp there anymore. Maybe it's some other type of like there's a river over top of it. It deposits a bunch of sand. And then there becomes a layer of sandstone. And maybe another river, right? All of a sudden, it's being covered and it's being put under pressure by more land on top of it. But what happens when you add not just 10 feet of new land on top, but let's say you add 350 feet of additional rock on top of it, right? What happens when you add 1,000 feet of rock on top of it? Now you're under immense pressure and the heat is building up. And all of a sudden, this peat, which is fibrous and discernible, you can pull it apart and kind of tell what you're looking at. You could even identify the species of plants with the aid of a microscope. Now they begin to undergo change. First into a type of sedimentary rock called lignite. Then they become under more intense pressure. They become bituminous coal. And then when those are subjected to metamorphism, so like if they undergo mountain building at the same time and it begins to warp and heat up that rock even more, it becomes a specialized, very high energy coal called anthracite coal. Now, I don't care that you know the difference between bituminous coal and anthracite. I just want you to generally know that coal in general is a type of sedimentary rock that originates from living plants that once grew in wetlands. Now, here's a bed of one of those in Alabama. This is a bed of lignite, and it's that blackish layer right there. And usually these are flammable. I mean, these are burnable. They are fossil. They're formed from living plants. They're fossil fuels, right? So, and here you can see overlying that is a totally different layer of marine clays, where the ocean, you had a transgression event. The ocean came up over that well. It'd be very much like having a swamp in New Orleans, Louisiana, that's near sea level. And then imagine when sea levels rise and New Orleans gets covered and a new layer of soil forms on top of it, it may form marine clays. And now that swamp is preserved underneath that as a bed of lignite all these years later. Okay, with that, what time is it? All right, we're just a couple minutes before break time, so why don't we take a break here? Let me see if anybody's got any questions first. Anybody online have any questions?
All good.
All good. Let's take a 10-minute break, and we'll come back just a couple minutes before 5:50. Okay. It's hot in here, isn't it? Yeah.
Hey, Dwayne,
Hey, what's up?
I didn't want to take class time with it, but I wanted to know the difference between diatomaceous earth and chalk. But I figured I could just Google it, but
You want to know the difference between diatomaceous earth and chalk?
yeah, because I've seen all the diatoms that make up the DE.
Right. Well, the biggest difference is diatomaceous earth is made up of diatoms, right?
Okay.
Chalk is made up of coccoliths, which they're both sort of unicellular. They both have that kind of, cool looking shell, but they're entirely different organisms.
Okay, that's what I'll look
But
into.
they're not, I mean, I don't know if it's accurate to say they're distantly related or similar. I'd have to go back and look at how genetically they are, but yeah, that's the biggest difference, is that they are entirely different organismal groups.
Okay, that's what I'll look into. Thank you very
Yep.
much.
You got it. Man, all of a sudden I'm so hot. Gosh, it's just, yeah. Yeah, I'm thinking, geez. Have to put a report in to tell them to turn that heat down a bit. All right, Jared. Yeah, this is all probably old news to you, buddy. I'm sure. Yeah.
Here it looks like tomorrow night be sun lingering. Tonight looks like have a rain till 2 in the morning, so. Might go out and look anyway, but I don't think it's gonna be good. Be better off getting more done tonight. Fast. Here, up here. See you later, man.
Get my rock collection out here.
You went out on the side of the road and that like this and started putting rocks in the mouth. How many do you think you can do before something falls over? Are you okay? I'll go. You try to do it. You go like make eye contact. Do it. Somebody like saying, singing this one.
Yeah, I got a whole bunch of rock samples here.
I was the sucker because they were playing rocks while I was doing the game. Oh yeah, you were definitely the sucker. Yeah, I was right. That's
Oh, you know what? They had them in the library. I'm not the library, but they had them in the bookstore for a while. I haven't checked there recently. I think you probably just get it online for Amazon. Yeah, I'll try that.
I checked the book where it said they learned them a while ago.
Oh, really?
It sounds about.
That happened to us last year. We had such a delay last year. That's why I scanned them and just put them on because, and I'm aiming to say, hey, grab them on Amazon because, you know, but, probably not supposed to do that technically, but. Exactly.
Yeah. Oh, yeah. Like on campus. You divided it up into 4 quadrants. You basically had to walk a beat and like report how many hours you did it, and then you dots on the map for 4 different species. And then you look like a creeper because you're walking around like over there where all the worms are with freaking binoculars. And people are looking at you like, who is this? Yes, and you would, like, right? Yeah, I did.
Okay, gang, it's 10 minutes goes by fast, doesn't it? All right, let's see. Is everybody back online here?
Yes.
Awesome. Okay, we just for those of you who are online, I've got my rock collection out here, and so unfortunately you guys aren't able to quite see it or feel these rocks, but I'm going to pass them around. We'll talk over a few of them through the rest of the class, and anyway, so you're missing out. That's what I'm trying to tell you. All right. Okay, so brought my rock collection up, and I'm going to end up putting this up probably somewhere in the class, maybe on the side desk or something. And I'm gonna label these so you can actually know what you're looking at, right? And what I would encourage you to do is, you know, walk around, touch them, examine them, feel them. Some of them are heavy, some of them are very light. Some of them are extremely fragile, like shale, and they can literally pop that easily and break it. And then right now, you know, just to yourself, how many of these rocks do you know? You know, are you familiar with these? This is one of my favorite right here because it's a type of claystone. It's very richly embedded with fossils of leaves. Anybody happen to guess how old those leaf fossils are? You have a guess? They're not carboniferous. I'll give you one more, maybe
Angiosperms or anything.
they're all angiosperms. I'm gonna pass them around actually. This is real fragile, so just kind of pass them around. You'll feel the clay content. Feel how smooth it is. Not Cretaceous, so it's Cenozoic. Cenozoic. These are from Tennessee. They are not marine, they are terrestrial fossils. These are from West Tennessee. And they, if I told you they were roughly 55 million years old, what geologic period and epoch would that be? You have anybody know? What do you say? Oligocene, good guess. You're in the right ballpark. Anybody else? Miocene, a little bit too young. Eocene, yeah, these are Eocene. And who can tell me, I think I already told you, right? The age, approximately 55 or so million years ago. So these are from the Eocene formations in West Tennessee. We actually mine these sites for clay. And the clay content is so pure, so rich that there's actually companies that extract those clays and use those to make things like porcelain. In fact, there's a company here in Clarksville. There's a corporation that's up near Exit 4 called Florum. They're an Italian company. And they get all their clay from West Tennessee, and they make bathroom tiles and backsplashes and all things that you could possibly expect out of porcelain and those things, which are all derived from clay because of the high content of a type of mineral called kaolinite, which is one of the important minerals in clay. Okay, so, and we'll go over more of these rock samples from time to time. I'll pass them around. In fact, right now, I'm going to go ahead and pass around one more set, just for you to kind of be looking at. This one here is probably been sort of sliced and cut a little bit. This is the nearest thing I have to Breccia. Okay, you can see that. And then the particles, if you feel that in your hand, you can tell that those rock edges are kind of sharp, right? Some of them are really at 90-degree angles. There's one on top. So it's a very sharp and it's concreted together, okay? Versus this one, all the rocks are still concreted together, but it's very smooth to the touch. So this is what? Conglomerate. Good. All right. So we'll start over here, Jacob. Pass these around. You can kind of get a feel for those. All right, I'm going to go ahead and lecture a little bit. Yeah, go ahead.
Are there deposits of clay or claystone somewhere that are much, much older than 55 million years and have been shielded from erosion?
Oh, sure. Yeah, for certain. I mean, there definitely are more buried clay deposits in various parts of the world that are underneath other more protected layers.
Hypothetically, if I wanted to have bath tiles made that were 500 million years old, I should
Sure.
shell out a ton of money to make that happen.
I'm sure somewhere they're underneath a more protected erosion resistant layer. Yeah. When you become a billionaire, yeah, figure that out, right? Yeah. Okay. So while the samples are going around the room, we're going to get back to it. We were on coal, as you remember, type of sedimentary rock. It's a biologic rock. And Juliet, remind me, why do we call this type of rock a biologic rock? Why does that make sense? Or plants, right? Either one, right? Plants or animals. Good. Let's see. Sarah, tell us what a clastic rock is. Yeah, man, it's like classic rock, man. No, not that type. Clastic. It's not a chemical, okay. So tell us what chemical is about. Just in layman's terms, what do you got? So the rocks form through chemical processes, right? Imagine you're in a chemistry class and you're doing like an experiment. You know, I was never good at chemistry, even though that's what my minor is in. I've had 5 classes, God-forsaken classes in chemistry. Please let me never go back to a chemistry class. I'm sorry, guys. I don't mean to say that. I shouldn't say that. But chemistry's not my thing, right? So, but think about, like, you know, you're in there doing an experiment, you're working hard, right? You're trying to get the precipitate out, right? To come out in solution. That's what we're talking about. You're talking about certain minerals precipitating out of a liquid or aqueous solution. And then those precipitate minerals accumulate, right, as they fall to the bottom of the water body that they're in. And they accumulate. It's the precipitate that accumulates, right? What is it not? It's not a plant and animal part. That would be biologic. It's not a fragment of a once former rock. That would be clastic, right? It's a precipitate. So that would be things like the ones we're about to talk about. So, by the way, one last image here of coal. That's a coal seam in a layer of rock in North Alabama near Birmingham. Okay, that blackish layer that you see there. Typically, coal is often very thin layered. It could be a few feet thick, but they are not in massive layers. And that should be obvious because they are so easily erodible, right? If they were in massive layers, they would simply just wash away, right? They have to be protected by other layers of more protective rock on top of them. That's why they have to be mined out. And so to get at that, you either have to have subsurface mines to go down and mine that seam out, or you have to do what? You have to take all the overburden off, the rock that overlies that coal layer. Remove it first. You've ever heard of mountaintop removal, right? That's what they're doing. They're removing the layers of rock completely off the top of the mountain to get to the coal seam. So they can save money and save energy, possibly save other things, lives, by not having to go underground. It's not as dangerous, but it's much more ecologically degrading to do mountaintop removal. Okay, so we're going to talk about 2 or 3 examples of chemical sedimentary rocks. The first one is Dolostone. Dolostone is formed of the mineral primarily as dolomite. And I think about that song by the Australians, making a Vegemite sandwich. Make a Vegemite sandwich. Well, we're talking about a dolomite rock, all right? So dolomite is the primary mineral that forms Dolostone. And it is has a high degree, it's very similar to limestone, which is primarily made up of calcium carbonate. But in addition to calcium, it has a high degree of magnesium, which makes it different. And there's really not a visual way to differentiate these rocks. In fact, I'll show you. This is not a perfect example by any means. But like, you know, here, this is sort of darkened piece here is a piece of dolomite from Alabama. This lighter piece is limestone. But I could also show you plenty of pieces of limestone that are kind of dark gray like this, right? They have a similar weight. They're both heavy. They're just never easy visual way to conclusively tell what you're looking at. So does anybody have an idea of how you would differentiate these rocks? Because there are important differences that matter. Like there's a whole site in Alabama, I'm going to tell you about in a minute, where there's a whole bunch of species that are only found on dolomite. They never occur on limestone. So the properties that they exhibit, that they have, they actually matter to living organisms. How would you tell these apart? Ian, do you know? Okay, anybody? Different hardnesses. They're similar in their hardness. They really are. Say again?
Salting it, does that count?
Yes, absolutely. And how would you do that?
I use weak acid.
Yeah, using a weak acid. That's right. So a weak acid, if you apply like some diluted hydrochloric acid, which I know hydrochloric is strong, but it's highly diluted, and you add that to say limestone will fizz you'll have a chemical reaction. So it'll begin to eat away or degrade that limestone because it's undergoing a chemical reaction. But dolomite, on the other hand, does not fizz when you apply the weak acid to it. So that's the primary way that we differentiate it. I know that's, to us biologists who like to feel stuff, the idea of taking around a little acid bottle and dropping it on rocks. By the way, I ordered one, but the snow delayed my acid bottle from getting here. So otherwise, we'd be actually doing the fizz test. I promise as soon as it comes in, I'll bring it in. We'll try it out. All right. And again, the reason I called on you, I thought you had an acid bottle that you use in the lab over there.
Yeah.
Okay. Have you done it on these rocks before? Got it. Okay. So Dolostone is fairly common in certain regions. The Ozarks of Missouri. If you've ever canoed some of those rivers over there, like the Current River or the 11-Point River, those rivers are lined by cliffs that are rich in dolomite. They are dolomitic cliffs. Down in Alabama, there's a river called the Cahaba River. It's primarily dolomite. Knoxville has got a lot of dolomite, but not around here. Most of our rock here is all limestone in this particular region. Okay. Now, you can also have mixed combinations. So rarely do you have pure dolomite or pure limestone. Often you have limestone mixed with dolomite, in which case we might refer to it as dolomitic limestone, right? And you can have various combinations. So it's rarely pure. And the processes of how dolomite formed are not well understood. You know, we talked about limestone is thought to have formed in a shallow sea that's kind of, you know, temperate to, or subtropical rather, or tropical. Let's read real quick about the depositional process that is thought to give rise to dolomite. Okay, dolomite is found in sedimentary basins worldwide. It's thought to form by a post-depositional process. So basically, after limestone is formed, some of the elements in limestone are replaced with magnesium through a chemical process. Okay, that means after that post-depositional process. So there's alteration afterward of the lime mud and the limestone by magnesium-rich groundwater. That is thought to actually form, create Dolostone. But it starts out as limestone, or it starts out as limey mud, and then it's transformed into Dolostone later. That's why they have a high degree of similarity. Okay. Now, Dr. Estes, I don't know that I want to know what Dolostone is. That's cool, guys. Just hang tight, man. Whew, it's getting hot here, isn't it? Here's the reason why. Okay, I want you to know something about Dolostone and limestone and all this stuff. A few years ago, there was a botanist from Georgia who was he was asked by the U.S. Fish and Wildlife Service to do an endangered species survey, and they said, "Jim, we're going to give you, $10,000 to go do an endangered species survey for this rare little mustard plant. It grows only a few places in Georgia and Alabama. And it's called a status survey. We want you to go out and determine how much is left and where does it grow and what habitats is it in and all this stuff, right?" Jim says, "Fine. Yeah, I know a little bit about that plant. It's called Arabis georgiana, the Georgia rock cress." And so he starts doing a literature review, right? Reading up on the plant, finding out where people have documented Georgia rock cress in the past. And one of the rivers that he discovers that somebody had made a collection on long ago is called the Cahaba River, which is down below Birmingham. If you're going to Florida on I-65, you cross over the Cahaba River. So he talks to a friend of his. He said, "Hey, I got a job to do, a consulting job. You want to join me? We'll go take a canoe trip down the Cahaba River." His buddy Tim says, "Man, that sounds like fun. Yeah, let's do that." So this is about 93, 94, 95. I'm in high school, just chilling out, just trying to get by. With Jim Allison and Tim are heading down to the Cahaba River on the weekend to have some fun, drink a few beers, do some plant surveying, make $10,000. Kind of sounds like fun, right? Not a bad gig for somebody with a biology degree, right? So he goes down and they're canoeing this river. We got pictures of it, right? I'll even show them to you later in class. They're hopping down this river and they're like, "No, Tim, left, right, Tim." And all of a sudden they're making their way around this bend in the river, trying not to tip over. And there's this really cool rock outcrop that comes down to the river on the right. And Tim's like, hey, whoa, whoa. And Jim's like, yeah, don't tip over. Let's get over that rock. Let's go check it out. Might be some Georgia rock cress over there. So they scoot over and they hop out, scramble up the rocks, get up there. All of a sudden they see that cactus. There's a palm tree. I mean, I'm not kidding. This is not hyperbole, right? And it's all rocky and desert-like. And these rocks that they look at, they pick them up and they're this kind of grayish rock, you know. And then the strangest thing happens. Jim Allison is one of the best botanists of the 1990s. Arguably one of the best botanists that the southeastern U.S. has ever seen. He's walking around. What does he see? He sees, Tim, I don't know what this plant is right here. I've never seen it. He bends down and takes a sample. It looks like species A, but it can't be that because of this and this character. Huh. Tim, I don't know what this is. This could literally be a new species of science. Wow. Hey, oh, Tim, wait a minute. Wait, Tim. Whoa. There's another plant here. I have no idea what this is. I have no clue what this is. They walk on. Hey, whoa, I got Georgia rock cress right here. We found some. They walk around. Whoa, I got another new species. Species number 3. Totally new to science. Gosh, I got species 4. Gosh, I got species 5. Holy crap, I got species 6. Poor Tim's not a botanist. He's just along for the ride. Oh God, I got species 7. You'll never believe it. I got 8 new species. They discovered. Not all on the same day. That's a bit of hyperbole. But over the span of a few weekend trips, they discovered 8 totally new species of plants, all found on dolomite outcrops, all within a 7-mile stretch of the Little Cahaba River of one county, Bibb County, Alabama, nowhere else in the world. So by 2001, when I'm an undergraduate at Middle Tennessee State, and from my undergraduate methods course, I have to pick a paper that I want to read. It's cool to me. I go to the library, never having been there. Select a journal, not really sure how to do this, right? Crack the journal open, don't even really know how to read this damn thing. And this first paper I read says, Botanical Lost World in Alabama. I was like, I want to read about that. Now, you guys have seen this advertised all around. You probably just didn't know what you were looking at. Because it's so famous now, it's even on the sides of U-Haul vans. You know how the U-Hauls are painted? Come to Connecticut. See our rhinoceros fossil or whatever, right? Come to Alabama and see the Cahaba lilies, the lost botanical world of Alabama. And if you look on the side of the U-Haul van, they even have the chemical formula for the mineral dolomite. That's how important to the story it is. Dolomite bedrock there, it's called the Copper Ridge Formation, is what makes that rock type special, what makes that ecosystem special. Today, Bibb County, Alabama is recognized as one of the top biodiversity hotspots in all of the southeastern United States. Isn't that cool? Yeah, rocks matter. All right, let's talk about one more type of sedimentary rock. So this next one, while we do not have a lot of dolomite in this region, we have a lot of this type of rock. This is called chert. Now, if a bunch of people around here kind of refer to this as flint. It's really, flint's a little bit different, but they're kind of similar, but it's technically we call it chert. And it's also a chemical rock. And like dolomite, it has a complicated way in which it forms that is frankly not well understood. So let's read some of this blue text here. Chert can form when microcrystals of silicon dioxide grow within soft sediments that become limestone or chalk. In these sediments, enormous numbers of silicon dioxide microcrystals grow into irregularly shaped nodules or concretions as dissolved silica is transported to the formation site by the movement of groundwater. So it has to do similar to dolomite, with where you have one substance laid down, groundwater moves through it and transports minerals into and out of it and transforms that mineral into something different, right? There's a chemical process that's really driven by the interaction with groundwater. If the nodules or concretions are numerous, they can enlarge and merge with one another, form a nearly continuous layer of chert within the sediment mass. And the chert formed in this manner is called a chemical sedimentary rock. Listen, I'm not going to go into depth on this beyond what I just did, right? I'm not even going to ask you on a test beyond the level of, is this a chemical sedimentary rock? It's really not for us to know the details of exactly how chert forms, but I want you to at least be exposed to it, okay? What I want you to know, though, more to the point, is how does chert differ from limestone, right? That's a useful thing to know. And what kind of properties is associated with soils or landforms that form over chert versus over limestone? Okay, so I'm going to pass out another set of a couple of rocks here, okay? This first rock I'm going to hand to you is, and I'm not passing the dolomite out because again, we have to have weak acid to identify, right? So, but this rock is a type of limestone too. Now, notice these are both limestones. They're both similar in weight. This one's slightly heavier, probably because it's more of a continuous mass. This one's got a lot of cavities and sort of holes in it. But this one's gray, this one's red. And that has to do with the mineral composition. This one's got, in addition to calcium, it's got a lot of iron in it, which is colored this red. All other things aside, these are both limestone. This has fossils in it, just like that. In fact, if I turn this around, you see that big Archimedes fossil right there. Okay. I don't have to know Archimedes. No, you ain't got to know that. Now, I want you to notice how limestone has these smooth angles to it, right? You're not really going to cut yourself on limestone, right? You can bludgeon somebody, but you're not going to cut someone. However, with this rock, this is a tool. This has been a tool for all of the Stone Age, right? Native Americans would pop that thing and pop it off, and all of a sudden they have a razor sharp blade. It would slit anything, cut meat, shave your hair, right? So chert, when it breaks, it has these naturally flat planes, and it forms these very sharp edges naturally, okay? So that's a key difference visually, where you can tell chert and limestone apart is just based on that picture right there alone. Chert and limestone.
Chert, bone pools.
Yeah, absolutely. That's what we use as primary. Now, different cherts have, some of the cherts are a little gritty, and you can't make a good tool out of it. They just brittle and break. Other chert is very pure. Those are the ones you can make spear points out of. Maybe, I don't know.
I know.
Right. Probably so. I'm not as familiar with that. Yeah. All right. Anybody online have any questions so far?
Not here.
Okay. Are you having any trouble hearing us as I storm around the room?
Nope, all good.
Great. Perfect. All right. I'm gonna stop asking. Okay. So chert. Now let's take a look here. This is a cliff face in at one of our state parks, actually. Sarah, this is the Burgess Falls State Park, which is about 50 or 60 miles east of Nashville. And what I want you to notice are all these bands or layers with that very sort of sharp edge to it. It's like a right angle, right? And each one of those layers, as they break off, they leave that very sharp edge. Well, that's chert. That's what those are. That's a big bed of chert. And here's what it looks like again, sort of up close. So in addition to the visual differences that I just mentioned, chert and limestone, there also is a very real difference in ecologically. Landscapes that are underlain by chert tend to be up high. And that's because chert is one of our strongest and hardest rocks. It's very, very hard, which means that it's also very what? well, if it's super hard, it's resistant to erosion, okay? So you're going to expect it on the tops of hills, the upper slopes of mountainsides, the crest of a ridgeline, right? And it also weathers because of it has particles of silicate materials in there, silicon. It also weathers into particles that are not rich in calcium, right? Because it's not like limestone that's very calcium enriched. So as a result, whereas calcium weathers into naturally a rock that's high in alkaline bases, right? Like calcium, and the soils that are derived from limestone are calcium rich, they're base rich, right? So they're naturally going to be good for agriculture most of the time. Not chert rocks. Cherts are weathering into some of the worst soils possible. They're completely nutrient deficient, very nutrient poor. They are highly acidic or moderate, usually strongly to highly acidic. And therefore they are not good for growing things like crops. Okay? In addition to the fact of where they are topographically, limestones usually are kind of down low, not always. Cherts tend to be up high on the slope. Right? So there's those key differences. They support quite different vegetation as well. Okay, here's what we're talking about. Here's a bunch of chert rocks here. You can see if you live in any of the counties sort of south and west of Clarksville, these types of rocks are very common at the surface. Some of the best areas that have particularly good pure forms of chert have been sought after by Native Americans for thousands of years. And those sometimes have been used again and again through the course of time. They've actually been deliberately sought out as quarry sites, is what we would call that. These are Native American quarries. And what a lot of archaeological research has shown that Native Americans were very much aware of where the best rock formations were. And so they might, for example, use a type of rock that today we would only find in one select part of, let's say, Stewart County, Tennessee, right? They might have a quarry that they went to on the side of a hill where it was an outcrop of chert that was so pure that it made the best spear points and arrowheads, right? Well, then another group of Native Americans, let's say living in Missouri, they would have their own quarries, oftentimes of chert, but sometimes of different kinds of rocks like quartzite. And they would then have these very select places they would go. Native Americans living in the Northern Rockies would often make their arrowheads and spear points out of obsidian, which is a type of igneous rock formed by volcanic activity through lava. We don't obviously have that in the East, right? We don't have any obsidian, but the Rocky Mountain Native Americans would have these quarries, and then through trade networks, that's how, in some cases, there's a few cases where they've actually documented these trade networks extending across the country, to where Eastern Native American tribes would have some obsidian in their possession. They could have only gotten that through these trade networks with Western tribes. And very commonly, they were trading other things as well, like copper, for example, was being traded by the Native Americans of the Great Lakes region with Southern tribes and so forth, just in very much the same kinds of ways that they would also trade other goods like, tobacco and corn and beans and various types of agricultural plants eventually came here through trade or were developed here, as we'll come to find out. So these rocks that were used for making, in our region, were primarily chert for making these stone points. We call them projectile points. And archaeologists, in some cases, have actually identified the exact site from which these rocks are derived. Now, they can do that through stratigraphy and through elemental analysis of those rocks, right? You can determine precisely the origins of some of these rocks. So that really is a key way that archaeology and geology sort of connect here, is in that one example. Now, I'm gonna go one step further, and we'll come out and cover this more in detail later. There's been some great studies out of Illinois, specifically using chert spear points. And they've recovered them from throughout the state, particularly in the time period stretching from like 9,000 to 12,000 years ago, when the first Native Americans were hunting in those regions. And they can glean even more information out of that than we could probably imagine. They can tell, for example, what size animals were being killed, right? They can tell a lot about the sort of population dynamics of some of those animals. In some cases, they can infer when the switch over from hunting bison transition into, say, hunting deer, right? The loss of bison, and then you see as they change to hunting other organisms, a change in spear point technology changes, right? These are all wonderfully recorded in the archaeological record. But one more fascinating piece, and I'm going to drop it here because I want to come back and touch on it later, but I'll just kind of plant the seed, is they have even been able to unravel the patterns of hunting migratory caribou in Illinois during the ice ages, and they can tell the migratory patterns of Native American tribes migrating north and south from the Wisconsin border down to southern Illinois in response to seasonal fluctuations in seasonal changes, largely following the migrating herds of caribou on the front face of the glaciers that had roamed south to about Chicago. And they can do all this by looking at spear point structure and technology. It's fascinating. So there's an amazing complex overlay between biology and archaeology and geology that we'll come back and talk about time and again. Any questions so far on that before we go into our second major rock category called igneous rock? Okay. Oh, one last thing. I want you to notice, Chert has one more thing that makes it super cool. So you saw that the Chert breaks off in sort of these flattish angles, right, with sharp edges. They can be razor sharp. But one other thing is, notice how along the edges, one thing that makes it possible to make these edges serrated through the flaking process of forming these stone tools has to do with a property of Chert rock called conchoidal fracturing. So notice this larger Chert rock in the lower right has this sort of indented concavity to it, right? There's a concavity here, there's one there. And that has to do that when you apply pressure to it, it breaks off a flake. If it's left to just natural breaking, it often breaks in sort of flat planes. But when you apply pressure to it, like if you're trying to flake the edge to make a stone tool, it breaks it off with a concavity. And that specialized way of fracturing is unique to Chert, and it's called conchoidal fracturing. I believe obsidian also has it, though, as well. Yeah. You can do it. That's right. Yes.
Yeah, that's like
Yes. And that's a great point about glass. Native Americans, when Europeans first came to America, one of the things they brought were lots of other kinds of artifacts, right? They would bring things to trade, and glass beads were one of those. And eventually they brought other types of glass. And oftentimes that was preferred by Native Americans in that European transition period to making arrowheads. And then when they started putting electric poles, this is really wild to me, like in places like New Mexico and Arizona and West Texas in like the 1880s, 90s, and they would use these certain types of glass insulators. They actually had a real problem with Native Americans would climb those poles and confiscate those glass insulators and make their arrowheads out of those. This is in the desert Southwest tribes particularly. All right, let's switch gears. Let's talk about igneous rock. Okay. Now, I have very few igneous samples, unfortunately. I have a couple, but these are the rocks that are formed from the solidification of magma or lava and volcanic rocks. Now, in our region, as I mentioned, we don't have any active volcanoes, right? Nor have we had any active volcanoes for probably safely at least 400 or 500 million years. It most likely is a little bit more than that. When you get back into the time frame, as we'll come to find out in a couple of weeks, like in the 1 billion year mark or 2 billion year mark, That's a very long time ago, but we definitely had some volcanism going on in certain places. So today, the granites, or excuse me, the igneous rocks that we have largely have been brought here. These are not the igneous that forms from a volcanic eruption. Those you would see in places like Washington State and Alaska and Hawaii, California, where you have a fairly active, existing volcanoes that exist as part of the Pacific Ring of Fire. In our region, though, the igneous rocks we have, and I'll just call out a couple types. We have things like granite and rhyolite, gabbro. Those are a few types. Those are primarily found where deeply buried magma chambers, like I'm talking about miles below the surface of the earth, that were originally formed like far, far away, were brought here through plate tectonics and brought to Tennessee and North Carolina and Virginia through continents drifting and moving into one another and molding those rocks and heating those rocks up. So in many ways, these were rocks that, formed very long time periods ago, mostly over 1 billion years in this case. All of our granites are definitely over 1 billion years. Okay, so let's just look at one quick example of how sort of the commonest type of igneous rock for our region, which is granite, how it forms generally speaking, okay? So we have the Earth's crust here. And as you can see, there are some volcanoes at the surface, but way down below all these other rocks that form the crust of the Earth. When you get down to either near the mantle, okay, the upper levels of the mantle, the lower level of crust, where that contact zone is between the crust and the upper levels of the mantle, it's sort of a molten and eventually liquid metal. And it's in this marginal zone where that superheated rock is being heated up. That's where granite is really forming. What happens here is that this molten magma, as it cools into an igneous rock, okay? Now, if that cooling happens slowly, very, very slowly, then as the igneous rock is forming, it crystallizes. In fact, another synonym for igneous rock, say it with me, is crystalline rock. Crystalline rock, yeah. In fact, when we talk about ecoregions late next week, we're going to mention a region of East Tennessee and North Carolina called the Crystalline Mountains ecoregion. And that's because it's formed primarily of igneous rock, okay? So as the molten magma is beginning to cool, it crystallizes. And those crystals actually continue to grow as long as it's still hot. And if it takes a long time to cool down, those crystals get a little bit bigger, a little bit bigger, a little bit bigger, so that they actually can be seen by the naked eye. Okay. If, however, that those crystals cool very rapidly, then those grains or those crystals in the igneous rock are small, and you really need like a hand lens or a microscope to be able to see them. Okay, and that's going to be an important part to classifying igneous rocks. Now, listen, we could get lost in the classification of igneous rocks real quick, and I got no interest in it, right? It's complicated. So we're going to just hit it at the high level. We're going to just act like we're geologists in the movies, right? We're in like active training right now, okay? Now, I'm going to pass around an igneous rock. This is granite, where you can actually see, and it's made up of different minerals. Some are light, some are dark. We'll get into all that later. But those individual grains that you're seeing here that look kind of like salt and pepper, those are the individual crystals that are large and visible to the unaided eye. Okay. I don't have my sample, unfortunately, of rhyolite, which is very small grains, in which case you would need a magnification. One last point. When you're looking at rocks, sometimes it's necessary to look at a freshly broken surface, right? Because if you're looking at the outside weathered edge, it could have oxidized and it might have rust on it. Like in this case, it's kind of orangish. You often want to break that and look at the fresh interior for you to actually see what you need to see. Because otherwise, you're looking at a weathered surface that's been exposed for a long time. So coming around is a piece of granite, which is an igneous rock. And I want you to hold, when you hold this in your hand, I want you to look at that. And I want you to imagine how many miles below the surface of the earth this formed and where. Okay. That's called the Cranberry Granite, and it's from extreme northeast Tennessee near one of our beautiful state parks near Roan Mountain. And I want you to think about kind of where that was formed and how deep. I don't really know the answer to that, but we can look it up. All right. So now let's take a look at, we talked about with sedimentary rocks, depositional environment was important, right? Because that's where sediments were being deposited into a lake, into a bog, on a continental shelf, right, along a river. We're not talking about depositional environments anymore with igneous rocks. We're talking about formation environments, okay? Where are these igneous rocks forming, not being deposited? So let's take a look. Well, and I apologize for the slightly grainy appearance of this image. Again, this gets very complicated, and I do not want you to know all the details. We're going to just get the highlights, okay? There are some types of igneous rocks which form after being ejected from a volcano, okay? Those are what we call extrusive igneous. They have been extruded out of the surface. Then there are those that form below ground, and these are called intrusive igneous rocks. Most of what we're talking about here, and all of it essentially in Eastern North America, that we're going to look at and talk about will be intrusive igneous. That means they were formed underground. Something happened that brought those rocks near to the surface. All the layers above it washed away, exposing those igneous intrusive rocks, right? Kind of like what you were asking about earlier. And then you've got lots of different settings. So, you have some that are kind of nearer to the surface, like immediately under a volcano. A lot of them may be sort of this molten, isolated, almost like how, this perched layer. You can have some that are massive, huge underground magma plumes or chambers. And then still others that can form where fragments of crust are kind of broken off and swimming in and floating in the upper layers of the mantle. Each one of these can result, when it cools and forms, into different kinds of igneous rock. Some become granite, some become gabbro, right? Some become rhyolite, and there are many other kinds as we'll explore. Now, I'm not going to go too deep in this because I just, I don't want to get way over our head and get complex here. But here's just a few basic types. So these are igneous rocks. Again, grain characteristics, whether you can see that grain with your unaided eye is important. Notice that the one I sent you around kind of looks like these two, right? Yeah. It's classified as a granite, but like I told you with the limestone, how some of it's gray and some of it's reddish. Granite is hugely variable. Think about granite countertops, right? You go to Lowe's, granite countertops. Lots of variation. Some of them are pinkish and purplish. Some of them are browns and grays. It all varies based on where it comes from and its mineral composition. So what are some things that kind of keep important? Well, number one, you got two general groups of igneous rock. Those that cooled quickly. That means they cooled so quick their grains stayed small. So these are examples of fine-grained igneous rocks, right? Take a look at this basalt, for example. It's just very, very tiny grains, right? By the way, that's the primary bedrock or primary rock that is found in the crust of the ocean in the farthest, deepest depths of the ocean. If you were to go down to 5,000 or 10,000, probably 15,000 feet deep, and go below the ooze that coats the bottom of the ocean to the actual bedrock underlying the ocean floor, it's formed of basalt, right? Now, those mountains over in Missouri that I talked about, there's a lot of volcanism over 1 billion years ago in the St. Francis Mountains, south of St. Louis. They cooled very rapidly. They're kind of a pinkish rock. Those are all formed of rhyolite. So if you've been to Tom Sauk Mountain or some of those places over there, that's all rhyolite outcrops. Now we look at these down here. Large grain size. They almost look like salt and pepper or various colors. These are your coarse-grained igneous rocks. They cooled slowly. The grains grew larger. Okay. Now, the final thing I'm going to talk about here real quick is this shows relatively where in the crust these rocks form, right? So something like basalt, oceanic crust. You see that? Same thing for gabbro. Now, there's a key distinction about gabbro, which is usually it forms kind of sort of close to the mid-oceanic ridges. Y'all know what those are? Remember? Basically where in the middle of the Atlantic Ocean, imagine Iceland, right? Here's the United States. Well, we don't have to imagine, we draw. We got, let me just draw this out. Here's Greenland. There's Ireland. There's Scotland and England. There's France and Spain. A little bit of Italy there. And we got Africa coming around. And Arabia, etc. Right? And then don't forget about Norway and Sweden, Finland, and all that stuff. Denmark. And then we got Iceland. Something like that. Okay. Over here, we're Central America, Yucatan, Brazil, something like that, right? Big old lonely, wide open Atlantic Ocean. All right. Splitting down the center of Iceland is a rift valley. Iceland is literally being ripped apart, right? Because there are two tectonic plates that come together there. The European plate and the North American tectonic plate, I think, are coming together, but they're also pulling apart. So whereas some tectonic plates are pushing together or rubbing against each other, these are pulling apart. All right. Now, that tectonic plate, that boundary, plate boundary, doesn't stop there. It goes all the way up into the Arctic Ocean. It goes all the way down through the North Atlantic, through the equatorial zone, through the South Atlantic, and eventually all the way down, right? Now, what's happening along that zone? Kim?
Seafloor spreading.
Seafloor spreading, right. So you've got continuous volcanic eruptions happening thousands of feet below the surface of the ocean. And there's magma pouring out, right? Lava pouring out, instantly solidifying that cold, deep water. And as it solidifies, it's very heavy. It's molten metal. It's rich. A lot of that is forming this oceanic crust rock called basalt. Some of it, which has a different mineral composition, is forming into a rock called gabbro. And that's where these rocks are primarily forming. And so what's happening is every time this is cranking out fresh magma, fresh lava, it cools, then forms a seam of new rock. And then you go a few years or whatever, it's continuously pouring out. It's pushing out new rock on both sides all the time, right here, up here. And all this pushing is doing what? It's leading to the seafloor pushing and spreading this way. And that, as we'll come to see when we get back in this topic in a couple of weeks, is contributing to the movement of continents apart, or in some other cases, pushing them together, right? Because that's pushing Africa and Arabia together. That's pushing North America closer toward Asia, right? It's pushing South America closer to Australia, that seafloor spreading. Now imagine that's also happening in where? Parts of the Pacific Ocean, parts of the Indian Ocean, right? So you got all these seafloor spreadings and junctions and everything, which is driving global continental movement and migration. So when we start talking about gabbro formations on the top of the Smoky Mountains, not really the Smoky, but Roan Mountain, when we talk about granite rocks up there, you got to stop and realize where those rocks originally formed. They didn't form in North Carolina, right? They may very well have formed at the mid-oceanic ridge and then migrated to their current position over hundreds of millions of years. And that's where we see them today. Now, why don't we take a break there? It's 6:40 and we got 1 hour of class left. We come back. Just one last final point here is that the continental crust, as you can see, these types, some of these other types of rock here, like granites and diorites and rhyolites, etc., they form as part of the continental crust, not part of the oceanic crust. Let's stop there though, come back and we'll pick it up with a few other things on igneous. And then hopefully we'll get through metamorphic in this final hour. All right, 10 minutes. Ian, is all this stuff familiar to you? Good. Good. Yeah, good. Okay. Is anything contradict? Okay, good. I don't want to contradict. Okay. Hey. Yeah. Yeah.
Can you explain that original that like what you did?
But which one again? Oh, right. Yeah, because she went there, didn't she? Yeah, right. It's a good book, man. It really is. Yeah, definitely. Well, hey, you're one of the few people I met that's read that book. So, I mean, I know others that have, but it's a great book, and she had a lot of fun going around and touring different sites and stuff. And yeah, the Cahaba area is incredible. Yeah. Yeah.
I don't really want to go kayaking that.
It's amazing. I mean, I thought about it even as a class field trip, but it's a good, I don't know, from here, it's probably four hours away. It's not super far, it's doable. I'm going to run and use the restroom real quick. Back, pass out some more rocks.
filling up that break as long as cameras every 30 yards.
Yeah.
And you'll see the bobcat will show up,
Uh-huh.
and then in between like the same 30-yard section, you won't see it on the next camera. So I think there's a trail somewhere that it uses, and the same with the coyotes too.
That's incredible. And so y'all doing bat work out there too?
I have before, but
Yeah.
it's kind of funny.
Hmm.
I set up for, the Coop Six
Uh-huh.
and I got nothing at 3 of them, but
Yeah.
one, it's like they're crossing right there.
Hmm.
Now I have to pull up the location right along the creek, but,
Are they crossing near that utility line corridor or not so much? They
I
cross,
think they are.
are they?
I think that is where it was, yeah.
Yeah. Wow. And, you got a gray bat out there one time, didn't you? Think so? Yeah.
One gray.
What other species would you expect out there?
Well, that's a pretty legit closed canopy stream, so
Mhm.
pretty much everything but big brown.
Okay.
And I was actually really surprised with auto gray because it's kind of a pretty good distance away from, what I know of as the roost in the area.
Mhm.
They're very picky,
Mhm.
so, yeah, I was surprised by that.
That's very cool. We have a new site that we're accepting almost 500 acres of land out to the west of Clarksville. It'll be a new state, it'll be a new, university property. And it's got a couple of caves on it. One's a big pit cave. And you can climb off. I mean, I've not been in there, but it'll be cool to see if there's any, as we continue to work with Katie and her students, see if anybody wants to explore that, and document anything. A lot of forests on there too.
The state of Tennessee would probably love to know.
Yeah.
James Dustin, he does a lot of cave surveys in the area.
Okay.
The only known gray bat roost around this area that I personally know of, and there might be another one, but, is Bellamy Cave out on Noble Road.
Okay.
I think there's about 3,500 out there.
Is that, down along the river or not so
Uh,
much?
I don't think it's
Okay.
close to the river. It's right across the road from Fort Campbell.
Gotcha.
7 miles off to the opposite
Well,
side.
that's probably close to where we're talking about. You know where the landfill is, right? This property is directly across the highway from the landfill. So,
Okay.
and there's an existing state natural area that touches it. It's called Barnett Woods State Natural Area. It's got 2 big cave entrances. Dr. Andy Barris, who used to be here and studied bats and had some students who did bat work back in 2007 through like,
His equipment's still in, Dunbar.
still in Dunbar Cave?
Yeah.
Is it really?
Came across it, February.
Wow.
We're out there doing survey.
Oh, I forgot they did a lot of work out there. Well, they also used to survey this cave out to the west of town. It's called Foster's Cave. Yeah, and that touches this property on the side. But we're about to restore 300 acres of prairie out there.
Gray bats aren't actually that susceptible to white nose.
Really?
Yeah, they're endangered for a lot of other reasons.
Okay.
They used to be full of, Dunbar Cave used to be full of gray bats. The reason they're not there anymore is because humans would go in, whenever it's owned by the
Yeah.
Star,
Right.
he would pay teenagers to go in there and kill them with, fence racks
Mm.
all the time.
Somebody built a fire. I think I heard they built a fire. They did something in Foster's Cave,
Mm.
which I don't know. I can't remember all the details. All right, everybody online here, we're getting ready to start back. Any questions?
Nope, all good.
All good. Okay, sounds good. Let's see who we got here. Good deal. All right, next up then we are it is so hot in this classroom that, I mean, we're all just smelting over here. It's like a damn igneous rock formation party up in here.
You ought to take your shirt off.
Take my shirt off. Yeah. Laura, you're so funny. We will not be doing that. I promise you. All right. So let's get back to it. We were on, yeah. So again, I believe in repetition. We get it, buddy. You done repeated yourself about 10 times. Well, repetition's important, right? Because it's the best way to like drill this stuff in your head. So hopefully if I say it 50 times, you'll you'll begin to get it, right? So coarse grained versus fine grained is a really good example of it right there. Just wanted you to see that a couple more times. All right, let's talk a little bit about mineral composition. And boy, I tell you what, I am not strong in minerals. However, you don't have to be in this class, right? It would be good to know a little bit more than what I know. It'd be good to get a little bit deeper. I mean, Ken, you're taking like mineralogy or something, aren't you? Petrology. And y'all get deep into minerals, right?
Yeah, I took mineralogy class.
You did, okay. Did you have to know hornblende and mica and all that stuff, right? Okay. And let's see, what's another one? What's a plagioclase? Okay. It would be good if we knew a little bit more about that, right? I'll strive to do better on the next class. But for right now, we're not going to get too deep into the mineral composition because I simply cannot, right? But what we are going to talk about is some generalities with minerals that, and I'm going to show you some rocks that help to illustrate these points. So number one, I want you to think about igneous rocks from a mineral. We already said you could divide them into large grain, small grain. That's one way to classify, right? Another way, though, is based on their mineral composition. So there are those which are relatively light-colored granitic, light-colored igneous rocks, such as granite. Okay, that's relatively a light-colored rock. Where's that sample of granite that was going around, by the way? Yeah, this one, you know, yeah, relatively speaking, right? I mean, it's got a lot of light-colored grayish elements in it. Now, it also has a fair mixture of darkish or blackish colors in there too, right? That's what I'm talking about with those different minerals. Some of those which impart that sort of lighter coloration to it, those minerals collectively make this what's called a felsic rock. That's a very important term that you need to know. Felsic. And generally what we mean by that is that these are light colored rocks with less than 15% dark minerals. Now, some of those dark minerals we could rattle off, and I'm going to show you some pictures of them in a minute. We'll get back to that in a bit. But let's contrast that with a type of igneous rock that is very dark or mostly dark. In this case, I don't have a sample of it, but basalt is a dark gray or blackish rock. So more than 40% is composed of, dark minerals. These rocks are called mafic, not magic. That's mafic, M-A-F-I-C. And then you do have those igneous rocks, which are in the middle or intermediate. You're never going to encounter this term again, but andesitic is one way you could say that. However, you will frequently, if you get into the world of, becoming an interpreter at a park, let's say, if you were to work at Elk Knob State Park in North Carolina and get a job, which is by far one of the most beautiful parks you can imagine, you will need to know the terms mafic and felsic. If you get a job at Dunbar Cave, you don't need to know those terms because there's no igneous rock at Dunbar Cave, right? It's all sedimentary. So, but these terms also convey real world differences in the ecologies of those areas. How so? Well, remember we talked about the distinction between chert and limestone? We said chert makes an area a little bit more what? Acidic. Felsic rocks are more acidic. They are less rich in alkaline bases. And so for that reason, the areas that are underlain by felsic rocks have acid soils, and they support vegetation that prefers acid soils. Things like pine trees, rhododendron bushes, blueberry bushes, right? If you have a high proportion of mafic minerals or dark minerals, there's a high proportion of base-loving or alkaline plants that prefer high levels of alkalinity. So mafic and felsic are definitely terms that you guys need to make sure you're familiar with. Now, as you can see, it's a complicated quantitative science in regards to figuring out what kind of rocks you got. So in addition to determining whether your rocks are like extrusive or intrusive, right, formed above land or underneath the crust, Then you also need to know things like how much light versus dark minerals they may have, right? And you may also need to know in what proportions, right? So, for example, you may look at these different types of rocks and they have different proportions of these different minerals that comprise those types of rocks. Okay? So things like rhyolite and granite, which are both acidic rocks and they're felsic because they have light colors, light minerals, have high degrees of these particular types of minerals. Orthoclase, quartz, they're sodium rich. They have a little bit of biotite, a little bit of amphibole, a little bit of muscovite. My head's gonna explode if we keep talking about minerals, Dr. Evans. Say it with me. I am not going to make you remember the minerals. All right? You don't have to remember the minerals. Well, now, Dr. Estes, I prefer to disagree with you on that point, because I'll tell you why. Those minerals are exceedingly important when it comes to understanding soil chemistry and soil taxonomy. Hey, soils guy, I know what you're trying to tell me, okay? I'm trying to administer this at a high level, right, from my class. You teach it the way you want to teach it. But I'm going to keep it at a high level, and we're going to skim the minerals. We're going to leave it to Mafic and Felsic. But my class at least is going to be aware that this slide exists. So if they want to dig deeper, they can. Right? All right. Question.
What were the needs of this?
Yeah, think about extrusive is igneous that forms above land, like on top of the surface through a volcanic eruption. Intrusive is underground, like down in the depth of the crust above the mountain. That makes sense? Yeah. All right. Okay. There's lots of these kinds of charts. You can Google image them all and you can see them. But again, I mainly just show them here as another way to kind of illustrate this. Now, I'm going to introduce one last group, which you will frequently hear in the world of ecology. It's an important term. And so we've already introduced Felsic and Mafic. Now I want you to take a look at the term ultramafic, okay? Ultramafic is a rock that is super high in concentrations of certain types of minerals. Particularly, it's rich in minerals called pyroxene and olivine. And I'm going to point these out. I'm going to pass around a ultramafic rock. It is heavy. Okay. And by the way, this rock is an example of what we call a meta-igneous rock. Okay. Who knows what that means? Meta-igneous. You could just simply call it a metamorphic. That'd be appropriate too. Chase? It started as an igneous rock that was then subjected to the forces of metamorphism, right, through mountain building, and became a meta-igneous rock. So it just shows you connecting back to that rock cycle concept. So this next specimen of olivine, the common name that many people would sort of apply to this rock is serpentine. Remember in the very first lecture I gave, I started with that Buck Creek serpentine barren, with sloping, grassy mountainside. This rock comes from there, and it is extremely high in certain types of metals that are toxic to, not to humans to touch or anything, but to a lot of plants like high aluminum, chromium, manganese, cobalt. Those are very rich in these types of rocks. A lot of metamorphic rocks are real heavy. That's one of the characteristics of it. Now, where do you think that rock formed? Mid-oceanic ridge. That's where these minerals are the richest, and that's primarily where serpentine rock is formed, is along the mid-oceanic ridges at a pretty substantial depth of the oceans. Where was that rock found? Right there. Western North Carolina. Where are other places where ultramafic serpentine rocks are found? A couple of places in North Georgia, north of Atlanta. You got to jump all the way up into one or two places in Central Virginia, all the way up to just north of Baltimore, Maryland,
just west of Philadelphia, and on the island of Staten Island in New York City. That's the only places in eastern United States where serpentine rock occurred. What connects them all? All these rocks are part of sort of the backbone of the Appalachian Mountains, more or less, right? A little bit off of the backbone. So all these places where they're now exposed were pushed up when this mid-oceanic ridge was pushed into forming the Appalachian Mountains. I promise you, you might say, man, I don't understand what you're talking about. That's, you know, I don't even know what that means. That's going to be the subject of a couple of lectures. So it's coming. I just want to introduce it. Okay. All right, I think we've kind of hit the highlights on igneous. Here's a granite outcrop shown on the left, just as a way to kind of visualize what these might look like out in nature. That's a big part of what I want you to get from this class, is what do these look like when you see them in the field? Where are the places in our parks and natural areas and cities and rural countrysides? What do they look like along the landscapes that you're going to be traveling in and working in? These are all, we already talked about granite. We've introduced gabbro. I'm going to come back and I'll talk about these in more detail later. Again, gabbro here forming underneath the ocean floor, yet it is up at the top of Roan Mountain at 6,000 feet along the Appalachian Trail. All right, I'm going to skip by some of these other kinds and let's go right to metamorphic. When we have the detailed discussions on the formation of the Appalachian Mountains and the Eastern North American continent, we'll revisit some of the stuff on igneous rocks and metamorphic. Okay. Any questions on that? All good? All right, metamorphic rocks. When you take a sedimentary rock or an igneous rock, then subject it to the forces of mountain building, right? And who can remind me of the term that we use to say when the building process of a mountain range, what is that called? It is a process of uplift, but it has a very specific term. Anybody else? All right, that term is called orogeny. And the plural is orogenies. Okay. And orogeny, so for example, the Appalachians were built by at least 3 orogenies: the Grenville orogeny, the Taconic Acadian orogeny, and the Alleghanian orogeny. So it kind of has either 3 or 4, depending there. So the rocks that were caught up in that mountain building process, like being pushed from the floor of the Atlantic Ocean by the collision of Africa, right? That's what was driving. Because Africa was colliding over and North America was colliding over, and they crumpled into one another, and their continental plates buckled and shifted and uplifted, to the term you just used. And through that collision that happens with all those rocks, they faulted and they broke, and so you got all these fault lines, and they folded and they fractured, and they heated up and they deformed. Some of them partially melted to the point where sand grains, for example, melted under that pressure. So sandstone transformed, or what we call metamorphosed, into its metamorphic equivalent, which is quartzite. Limestone, the sedimentary rock, when heated up, forms into what? Marble, like a marble countertop or a marble column at a courthouse. Okay. All types of rocks can be driven through this process. So granite can be metamorphosed into a type of metamorphic rock called gneiss, which is spelled G-N-E-I-S-S. So how metamorphism happens? Well, it can happen through being buried, like in the case of coal formations, can be buried over time by other types of rock layers, and through the mountain building processes that we talked about, through orogenies, or it can have heat and pressure coming from underneath, such as if you have a plume of mantle, which is like a giant bubble. Think about that. A bubble of liquid metal bubbling up, pushing against the lower surface of the crust. And that pressure and that heat from all that molten rock also then heats up the area above it. You might think, that doesn't even make sense. Well, it should make sense, and here's why. Remember density, right? Just give me the basic tenets of like two objects. Which one's more dense? Which one's less dense? What do they do when they meet each other? They separate into layers. And if they're in liquid form or whatever, which one's going to rise and which one's going to be on the top and the bottom and all that stuff? Less dense floats. Taking a look here, what can you say about density of the mantle of the molten magma versus the crust of North America? Which one's more dense? Which one?
Crust ones, or the molten magma.
So the molten magma, which is in liquid form, is more dense. That's why it's underneath, right? So keep in mind that those continents like North America and Africa and Europe and everything, right? They're floating on top of the mantle, which is entirely molten material, liquid, right? It's liquid nickel and iron and all these really heavy metals. They're even in a liquefied state, it's more dense than the crust above it. Isn't that crazy? So these continents are like floating, like icebergs in the ocean on top of the liquid mantle. Now think about that. With all that stuff that's happening under the mantle of like, you know, convection and all these terms which I barely can even fathom, you've got heat transfer and molten plumes are moving over here and over here. It's affecting the movement and the dynamics. Things happening in the molten magma underneath are affecting how the continents move. All those heat exchange dynamics. That's a whole other class that we're not even going to begin to get into. But the key point here is that the crust floats on top of the liquid mantle. And that, my friends, is going to dictate a lot of stuff. For example, those little fish in the Caney Fork River and the Collins Fork River, and some of those other rivers like the Calf-Killer River and the Obi River, they all went through that radiation. They evolved in the span of just a few million years. Why? Current research is showing that one of the reasons they evolved as rapidly as they did in separate river systems is because underneath Tennessee, deep underneath eastern North America, was a mantle plume, pushing the North American continent up, pushing Tennessee and the Appalachians and uplifting them slightly to rise because they were being pushed by a more dense molten magma chamber underneath, many, many miles below the crust of North America. And that uplift effect led to this one river responding by cutting down into the rocks more quickly. And it's through that cut down, we call down cutting, that led to the radiation or the evolution of this diverse fish assemblage right here in Middle Tennessee, where they became isolated. What drove that? Initially, it was a magma plume underneath eastern North America. That's why this stuff is important to biology. Now, you go read any paper you want on phylogeny or population genetics, biodiversity conservation, and almost none of them will acknowledge or mention these processes. Why? Why? There's a practical reason. Why? Well, how many of you are exposed to the basics, or to not even the basics of geology? If you're a biology major, right? Unless you go to the geosciences department and take more than one class, you're not going to get into this stuff, right? What happens then as you become a professional biologist, you get your PhD or whatever, you stay in your lane. You recognize your limitations. You don't go off doing research in geosciences or astrophysics if you're a biologist, right? So it often, we don't think about the need to be cross-disciplinary in our approach. That's the purpose of this class, is to open up our eyes a little bit to the cross-disciplinary approaches that we can glean from borrowing from archaeology to biology, or from
geosciences and geomorphology to biology, right? Because at the end of the day, there are tons of examples just like this, where geological processes are driving biological processes and phenomena. We need to be able to know that stuff, or know how to explore it, or know who to ask, or even to know what to ask. I wish you'd get down off your damn high horse and get back to teaching. I'm ready to learn something. I'm just saying, we got to talk to each other. That's all I'm trying to say. All right, what happens? What time is it? 7:11. We got time, yeah. What happens when you metamorphose a given type of rock? Well, let's take a look at granite, right? Here we have granite with its large crystals. When we subject that to metamorphosis and heat, then those minerals totally realign themselves, and it becomes sort of almost what we call striated or lined. So the dark mafic minerals here, those blackish minerals, sort of line up based on patterns of density. Lighter minerals accumulate in a certain plane, darker minerals in another. And so it changes that rock into a totally different rock type. So granite becomes gneiss. That's the way we pronounce it, gneiss. Now, it still has the same minerals in mostly the same relative amounts and proportions, but they tend to be arranged differently because of that metamorphism. All right, now what we're going to talk about are two kinds of metamorphic rock. We're going to classify metamorphic rocks just like we did with igneous, right? First things first, when you have metamorphism, you're going to have some examples that metamorphose into distinct layers. These are called foliated. Foliated metamorphism versus non-layered rock, non-foliated, okay? So these are both examples of types of rocks that are non-foliated. They do not form layers. Now, think about for a minute, what kinds of rocks that are naturally layered anyway would still stay as a layered rock if it's metamorphosed? Well, I'm going to show you one. Okay. Now, this one's very fragile, so handle it with care. I'll probably just walk around and show it to you, and then I'll pass it up. So this one is shale. If you'll notice, it's layered, right? All these layers here, you can actually just split that apart. Put on the sample. But that's an example of a foliated sedimentary, right? It's in those layers. When that becomes metamorphosed, it can become one of these types of metamorphosed rocks. What I want you to notice when you see this, by the way, this is called schist, and I've got a couple of them. So when you look at this, you'll actually see that it's heavy. It's got that typical heavy feel of a metamorphic rock, but it's in very distinctive layers to it, right? That means it's foliated in layers. Now, unfortunately, I have very few samples of metamorphic rocks to share, and I don't have any of marble or quartzite to share with you, unfortunately. But just trust me that these are non-layered or non-foliated rocks. Okay. This process of metamorphism changes the composition of the rock in this way. So take a look, for example, at sandstone. You have individual grains of sand, which is made up of the mineral quartz. And those sand grains, by the way, that's what makes up this rock right here. Those sand grains are cemented together with another mineral called calcite. And that's what kind of holds it together and bonds it together as a type of sedimentary rock. Now, this is what happens when it metamorphoses. Okay, those sand grains and those calcite grains, they heat up and they expand and they become deformed. So deformation, becoming deformed, is a common property of metamorphic rocks. Right? These sand grains or these quartz grains, notice how much enlarged they become, right? They also fuse together, okay? A lot of these interstitial spaces here, or what is made up of other types of cement type materials, gets melted as well. And so this is what the mineral composition looks like under magnification when you go from a sedimentary rock into a metamorphosed rock, okay? Now, here's an example from marble, starting out with limestone. Look at all those fossils there. Each one of those gets heated, gets deformed, obliterated, they expand, and this is what it looks like after it's been metamorphosed. Okay. All right. So in looking at metamorphic rocks, as I mentioned, there's two major categories, foliated and non-foliated. Let's first talk about the foliated examples. That's the one I've got kind of handing around. In this particular case, you've got all of these here are examples of rocks that are metamorphic. At the one end of the scale, you've got slate, and then you go through increasing levels of metamorphism, meaning the pressure goes up, the heat goes up, more intensity. So when things are barely metamorphosed, you take the shale and slightly metamorphose it, it becomes slate. If you keep turning up the pressure and the heat, it turns into phyllite. If you keep turning it up a little bit more, it becomes schist. And that's what I'm passing around now. If you turn it up some more, it becomes gneiss. If you go even more, what does it become? Pressure and heat, even more, above gneiss, you melt it. It's back probably in the igneous realm at that point, right? You're recycling rocks at that point in this part of that rock cycle, okay? Now, take a look at what's happening with the minerals, right? As they are being deformed, you can see that deformation happen. Now, I'm going to bring this back around as we go through this next series of lectures as to why this is important to begin with. Well, what do you know about metamorphic rocks? Where are you going to find them? You're going to find them here in Clarksville? Where should you go looking? Go to mountains. Go near Gatlinburg, right? Go to the Ocoee River Gorge. Go to Western North Carolina. These are places to expect metamorphic rocks, okay? You can't see them here. That's one reason I don't have a lot of good samples of them. All right, now the non-foliated types, we have marble, we have quartzite, and anthracite is that type of coal that has become metamorphosed that we talked about a little bit earlier. Okay. Now, with that, we have gone through sort of the first stab at an introduction to all sedimentary rocks in this region, the major igneous types and the major metamorphic types. Let me see if you have any questions, and no question is stupid, as we work our way through geology. Anything at all, or from the past lecture, before we continue on.
Metamorphosis has to be. Would there be a scenario where you could have high enough heat and pressure and some catastrophic, like the plates just suddenly shift and
good question. I think the answer probably is, again, being not a professional geologist, right, is that there are cases where it can be fast. And the one I'm thinking about most quickly is with meteor impact sites. So, for example, one of the signature marks of a meteor impact site is what's called shocked quartz. And so the quartz crystals or the grains that look like sand take on a very deformed, expanded appearance that are very diagnostic to anyone who studies meteor impacts. That's a form of metamorphism, right, where those particles are metamorphosed. So I'm sure there are other examples, but that's about the limit that I can give you on that. And the site here in Tennessee, the Wells Creek Basin, those shocked quartz, and another feature they have there is called shatter cones. Those are indicative of intense metamorphism from that impact, which is very immediate, right? Otherwise, this metamorphism we're talking about from the collision of Africa and North America, we're talking about a process that's taken place over like 200 million years, right? It's a long, drawn out process of metamorphism that's leading to that. In other cases, it's not as long. The Sierra Nevada mountains, they formed in probably less than 10 to 20 million years. So that's a relatively recent process of deformation that happens at a much shorter, but still long time period. Yeah. Anybody online have a question for us?
Nope, I'm good.
Got it. Okay. All right. So we got about, about 20 minutes left. And this slide, we've got a few slides left to go, about 20 or so. This is largely sort of kind of getting into sort of a review process here. So let's take a look, right? All right, everybody, first of all, if you would just kind of stretch your arms out, maybe get yourself stretched out, get yourself ready to kind of absorb some knowledge for the rest of these 20 minutes here. That way we're not getting too sleepy and tired. It's kind of hot in here. All right. Okay. All right, so just some quick review stuff here. Some pictures. Here's limestone, sedimentary rock type, right? But metamorphoses into marble on the right. And you can see where it's, at least at the naked eye level, it looks like it's been highly deformed compared to what maybe you might be otherwise used to seeing. Dolostone, dolomite, can also metamorphose, in which case we call it dolomite marble or Dolostone marble. Those are interchangeable there. So quartzite, when it is a type of rock that originally was sandstone. And as we said earlier, if you heat up those sandstone, those sand grains, those quartz grains, they expand, you get deformation. Pretty much all these things you probably need to look at with a magnifying lens, or you need to be a professional geologist. Now, there's one thing that helps us as non-geologists, and that's something you're going to become familiar with, and that is process of elimination. Okay. Now, if you need to become a paleontologist, you'd better be able to identify quartzite from sandstone. Okay, it's relevant to your study of fossils and stratigraphy and rocks. If you're going to be a natural historian or a wildlife manager or an interpretive ranger, it's probably good to know this stuff, but you don't need to know quite the same level of detail. So geologic maps can be your friend, because they can then map what rocks are in what specific place. And there's also some really good guides. For example, one of the guides I think I have in the suggested reading for this class is like a roadside guide to geology of Tennessee. And so it tells you wherever you stop at a certain interstate exit, go here and look in this rock layer, and it interprets what you're seeing, right? And so it's a very good way to kind of, even for the layman or not having gone through an official geology course, you can still learn a lot of the stuff about where these rocks are. Conglomerates can become metamorphosed into metaconglomerates. So this is oftentimes what you'll see is some sedimentary rock types, they'll still include that as part of the name, but then they'll put that prefix meta on there to indicate that it has been metamorphosed. So conglomerate becomes metaconglomerate. Sometimes, rather than calling something quartzite, you will see the term meta applied, and they'll call it meta sandstone instead. I have seen that. Gabbro, which is an igneous rock, when it becomes metamorphosed, becomes metagabbro, right? All right. Now, a minute ago, I said that particularly with things like the foliated metamorphic rocks, that if you wanted to see examples of metamorphic rocks, the best place to go is to the mountains. Let's take an example of shale. And what would happen if you took shale and subjected it to various degrees of metamorphism, and how that translates into the actual landscape, okay? So, for example, out here in this green zone, tell me what type of rocks you would expect there in the left side of this image, based purely on that diagram that you're seeing. What kind of rocks would you expect there? Sedimentary, igneous, or metamorphic? Sedimentary, right? They're kind of in flat-lying layers, right? Yeah. Now, let's say that this was like a river floodplain, and there was maybe some shale there, for example, right? This very thin-bedded shale formation. Now, if we wanted to go into the mountains, as we're looking at them in the distance, right? Looking east into the mountains. If we had that same layer extending into this region, or similar layers, because it's a mountainous environment, we might expect that shale layer or other layers that are similar to it in age have been metamorphosed and deformed. So while we might expect typical shale here, if we go into the western edge of these mountains, very much on the edge of metamorphism, we would expect to see the lightest degrees of metamorphism, in which case, that's exactly what we see. When we go into Gatlinburg, in the edge of the Smoky Mountains, we see the first stage of metamorphism exhibited by the rock called slate, which is used for making pool tables, the tops of pool tables. Slate. However, if we continue in just a few miles into the mountains, we encounter phyllite. If we go still deeper into the mountains, we get schist. And if we go about 50 miles into those mountains, we hit gneiss. Okay, that is a very simplistic sort of overview of it. But if you're looking for these specific rocks, for example, the Ocoee River Gorge of Polk County, Tennessee, anybody here ever been rafting on the Ocoee? Well, there's a specific set of rocks along the north side of the river called phyllite. And those rocks have a species of plant that has not yet been named, that's only on those rock outcrops and nowhere else in the world. So you might want to be able to try to find more examples of those phyllite outcrops to describe that species. Right? Okay, kind of talked a little bit about some of these things here. I've got some just different examples. That's all showing the shale to gneiss transition that we just talked about through those various zones. Okay, and again, they have different properties. A lot of this we'll kind of touch on as we go back. Now, let me just show you a few of these pictures sort of out on the landscape. These are slate outcrops up on the top of Mount LeConte above Gatlinburg. If you look down there, there's a highway, and that's the road that leads up through Great Smoky Mountains National Park to Newfound Gap. That's the main dividing road over the Smokies. And you can actually look up in places, and these are landslides where the highly unstable rock, slate in this case, periodically sloughs off and forms these avalanches or debris slides. You can see why that would be a big hazard for building roads and those kind of things, right? So when we get very high rainfall, sometimes coupled with small earthquakes, believe it or not, 2 or 3 on the Richter scale, they can trigger these avalanches of debris slides, and they can block those roads in some cases. And that's what slate looks like up close. Again, you can notice that it's in those foliated layers, right? So it's a foliated metamorphic rock. Phyllite is much chunkier. I wish I'd lost my sample of phyllite. You know, if you threw a piece of slate at somebody, it's just going to like disintegrate, right? It might cut their face a little bit. You take an equivalent size of phyllite and throw it at somebody because it's really heavily metamorphosed, you'd probably kill them, right? It's that heavy and that big. But notice it's still got these foliations to it, or those layers. But those foliations are what makes it really unstable, particularly when you take that mountain and you turn it up, right? So imagine if you're building a highway through a mountain range like Interstate 40 that connects Knoxville to Asheville, North Carolina. Every few years, they have major landslides that block the interstate for weeks at a time because of the phyllite layers. So as a geologist, you obviously need to know this. As a biologist, those phyllite layers support endangered, undescribed plant species that are highly localized to that outcrop. So it behooves us to both be familiar with it. There's a piece of schist. It's heavily metamorphosed. Its sheets are very tiny, almost like little silvery flakes. And then there's the gneiss, which is so metamorphosed, it's almost been melted and rearranged. And its minerals have actually migrated into these very distinct light and dark bands, like that. Okay, just 2 or 3 more slides and we're done. So this is one of my favorite rocks. This is a black, almost salt and pepper gray kind of a rock. I've got a little bit of sample somewhere. Yeah, here it is. Man, I used to have a great sample of this. I mean, it was like this big. I think one of my graduate students stole it or something. This rock is probably one of the rarest rocks in all of Tennessee. It is literally found in the northeasternmost corner of Tennessee. Imagine here's Tennessee, right? Here's the Smokies. Here's the Mississippi River. Up in northeast Tennessee, it's in this county. That's the northeastern county. That's Johnson County. If you were to look in at Johnson County and sort of magnify it, Johnson County has this cool little extension like that. Right? If you were to look at it on this map, you can barely see it at this scale. But if you look at it close up, you can see it. But what's really cool about that extension is when the first land surveyors were coming to survey the North Carolina-Tennessee boundary, they kind of got off track. And they walked up to the top of this mountain for a little bit, actually walked along the top of that mountain, and then they decided to go back over and get back on course. And when they did that, they mistakenly added a little bit of North Carolina into Tennessee. Otherwise, if they hadn't made that mistake, then we wouldn't have any of this rock type at all. But by making that mistake, the cool thing is they gave us just a little bit of the ridge line in the western slope of a mountain system that's otherwise entirely found in North Carolina. It's its own ecoregion. If you've been to Boone, North Carolina, where Appalachian State University is, Boone's about right there. And this ecoregion is called the Amphibolite Mountains ecoregion. It's my favorite part of the Appalachian Mountains. And Tennessee only literally has about a quarter mile and probably about 10 feet wide along the spine of one ridge of exposed amphibolite. But here it is. I'll pass it around. Notice that it's salt and pepper in color. It's very dark blackish. It's very mafic because of that high concentration of black dark minerals. And what does that mean? It's rich in bases, rich in things like magnesium and some other kinds of calcium and so forth. And it's layered, it's foliated. So there's a lot of really cool plants only found on amphibolite up in that region. We'll talk more about that later. All right, with that, there are some various self-tests online. You can take a look at this link, for example. If you want to learn your own rocks, you want to study some images online, I encourage you. But, you know, really there's nothing like seeing these things in the field, feeling them, touching them, and it just comes with some experience. Like I didn't know rocks when I started, you know, several years ago. I taught myself. So again, hopefully you guys will pick up a little something that's useful. That's all of today's lecture. And if anybody has any questions, feel free to stick around. We got about 3 or 4 minutes left. Anybody online with any questions?